Okay, I just want to show you two things on the website. So were these here before? Anyways, okay, so there's an assignment for Friday morning. Notes on vector video. So like, so we're not having the lab time, that extra hour and a half lab time, so I do feel like I can offload some lecture to videos instead, so that we can spend time in class doing more interactive things, you know. So the way this works, though, I just want to like force you guys to watch this video, so then you have to like take some notes and upload your notes. It's not that big a deal. I just spot check it real fast and give you credit. So you don't feel like you have to take perfect notes or anything, but I just want you to watch stuff. Because this like this basic stuff about vectors is like stuff I would just lecture about for like 20 minutes, and then you just sit here and watch me. So just watch it on your own, take notes, upload to Gradescope before class Friday. And but you'll definitely have a chance to ask questions, like if there's anything in the video that you like were confused about or want to follow up on. I'll start class Friday, like, how was the video? Any questions about that? You know, anything else you want to follow up on? And then, because then I've got this good vector handout that we can start working through, so we can go into group work. And that'll last at least Friday and Monday. I did last semester, and I did this. I actually assigned this video first, which is from another YouTube channel called 3 Blue 1 Brown, which makes amazing YouTube videos. It's like the only math channel I actually like. Like I don't know. It's like most math videos on YouTube I cringe at, but then these are actually really good. But this is actually more for a linear algebra class than for a multivariable calculus class. So I had assigned this, and then I made a few references to it in this video, but the references are not, you can just ignore them, because I think this might be more confusing. I mean, you can watch this because it's a good video, but it's more about linear algebra than it is about multivariable calculus. So it's a slightly different perspective on how we use vectors. So you just have to watch this one and take notes on it. But I put this one down here in case you want to look at it. Does that make sense? So I'm just looking for notes on this view. Okay. And it is like 20 minutes. Oh, 26 minutes. Sorry. Sorry. You know, you can click through. What is all this? I don't know. Sometimes it's just me talking. It's pretty low key. Okay, so just try to do that sometime in the next 48 hours. Okay, and then, oops, oh, you see behind the curtain. Right, so today, this is sort of the plan for today. Talk about linear functions a little bit. We're not going to spend too much time on this, and then functions of 3 variables. So let me stop the share and then just leave it on screen if you want. Yeah, quickly, because we were doing cross sections and contour map plots and stuff like that, right? But I want to talk about linear functions quickly, just because they're going to come up. We're going to do a lot of stuff with planes in this class, kind of like you have to kind of understand lines completely in the 2D plane before you start looking at more complicated curves. So we're going to end up understanding sort of planes completely. And we already mentioned the first day of class that the important thing in single variable calculus is the tangent line, and the analog in multivariable calculus is going to be the tangent plane. So we're going to want to understand planes well. So let's just go ahead and start talking about linear functions. And you can guess it's just functions of that form up there on the screen. So like the form is it's just a linear function of x and y, right? So you can almost think of this like the analog of y equals mx plus b. Nobody says this, but I kind of like to call this like slope-intercept form. Like we call y equals x plus b slope-intercept form, right? So this is like slope. There's like an x slope and a y slope form, I guess. yeah, we could sometimes we call this the x slope. And we call this and the y slope. Right. And I just wanted to sort of do an example and think about what the contour map actually looks like. So let's do something like z equals 2x minus y plus 4. Okay. So you could look at cross sections. You could set x equals constant, y equals constant. But let's look at what z equals constant, like what the contour map. Contours. Z equals constant. So like, we could just say like, what's the z equals 0 contour? Well, that would be 0 equals 2x minus y plus 4. And if you want to plot that in the plane, maybe you want to move the y over here, right? So y equals 2x plus 4. That is equals 0. We could just try a couple of different ones until we start to see a pattern. Z equals 1. I think that resolves down to y equals 2x plus 3. Is that right? If I subtract the 1 over here. Y equals 2x plus 3. Z equals 2. X plus 2. So you could almost guess, what do you think when z equals 3, we're going to get? Just from the pattern we see on the board. Yeah, y equals 2x plus 1. Good. You can do z equals minus 1. Minus 1 equals 2x minus y plus 4. So y equals 2x plus 5, etc. Okay, so if we want to draw the contour map, they're just all of these lines, right? So contour plot. Do I still have the screen share on, or did I stop it? I'll stop it. Okay, so we should be able to draw the contours now. 2x plus 1, I guess, is the, let me just maybe mark off some. So I need a slope 2 line. So like that, like that, and so on, right? And you could just sort of see, well, it's going to be like this, right? For different values of z. Yikes. Being a little loosey-goosey, but you could label this. So this was 2x plus 1 was height 3. 2x plus 2 was height 2, height 1, height 0, height minus 1, height minus 2. So the contour plot is a bunch of lines, right? And I think hopefully that should make some sense. Like, the graph itself is a plane since it's linear. And if you had a plane, we're going to do a lot of stuff in this class with like, there's going to be a lot of times where I'm like, pretend we're on a ramp and we're zoomed in, right? So the horizontal level curves are just straight lines, right, on the plane. And it's more just about whatever angle they're at. So you can sort of try to even imagine this plane like the tilt, like from above, like, because this is x, this is still x and y here. Looking from above, it's sort of like, oh, well, it's turned this way and tilted this way. Does that make sense? Because like these are going up in z value. Okay, so that's just the idea. The big thing to notice, I guess, the sort of qualitative statement I want to make is that the contours are parallel and equally spaced lines, right? Parallel, and it's important to say this, equally spaced. Lines. Because like, we can imagine a contour plot where the lines, where these go up like quadratically instead of linearly, something like 1, 4, 9, 16, 25, and so on. And that would be getting steeper and steeper. Or really the lines would be getting closer together if we wanted to always do, label the contours in a systematic way. So you can have curvy things that have, where the contour plot's still made up of lines. But in the case of a plane, then that's kind of what we're expecting, right? Make sense? Any questions? Okay. I thought about going backwards, which is if I give you a contour map of a linear function, could we actually find the equation of that linear function? And I picked this out of the book. And I just found this picture like in the exercises, I think in 12.4. And I'm worried now, this might be a little tricky, but if we saw something like this, could we recover the equation? Right, so if we see a contour plot of a linear function, those are parallel and equally spaced lines, right? Can we recover the function? Can we find the actual function? And the answer certainly is yes. It's just like a question of how. So how are we going to go about this? So let me go back to the board. I should just pause the share. That does. Okay, I'll just this. So yeah, I definitely could have come up with less tricky ones, but because also there's only a certain points, nice points these go through. But do any of those lines go through nice points? The second one, the 2000. Oh yeah, because it goes through this point right here. Okay, so we should be able to find the equation of that line, right? So we should be able to find like that's the question was we're thinking about level surfaces, like level curves, level curves. So yeah, so what's the equation of that line through that point? It's a little bit hard because we don't have 2 points, right? The 4,000, there's 2 points, so we can probably figure out the slope. Whoever said that from there, right? Yeah, so but the 2,000 we're going to use also because that's also, we're going to need a couple different ones for the spacing, but we could use recall point slope form, right? Y minus y naught equals m times x minus x naught, where m is the slope and x naught y naught's a point on the line. So here, what point do we have on the line? On the 4,000, the one labeled 4,000. 50, 300. And what's the slope? What's the other, using the other point, what's the delta y? The slope is 2/3, or well, negative maybe or something. Because the delta y is, if we use, I guess we have 5,300 and what, 200, comma 200. So the slope is 200 minus 300 over 200 minus 50. Is that delta y over delta x? Yeah. So you said that's minus 100 over 150, which is negative 2/3. Okay, so we do get, so one line on the contour plot is y minus 300 equals negative 2/3 times x minus 50. 2/3 here are a little bit annoying, but we can roll with it, right? It makes sense what I'm doing up to this point. Like I'm just having an equation of that line that's labeled 4,000. And you guys should check me and make sure I'm doing this right. We could also have used 200, 200 here instead of 5,300. Should work out to be the same. So let's just write down. Actually, there's some nice things you can do here. You can sort of like, we want to have mx plus ny plus, we want to find the x and y slope, whatever. So I could multiply by 3 over there and say we get 3y minus 900 equals negative 2x plus 100. I think if I multiply the negative 2 through there, multiply the 3 up over here. And so we get 2x plus 3y equals 1,000. And this is the contour at height z equals 4,000, right? This is the contour z equals 4,000. Okay, so I want to think about what that means. We're looking for a function like mx plus ny plus b. And we really want these two equations to be the same equation. We want this and this to be the same. So whatever this is should be equivalent to that, right? I think that means we can probably figure out m and n. Well, maybe. Actually, I should be careful when I say that. Because we have like one, we sort of know one line now on the contour map, but we don't really know the tilt of the plane. Does that make sense? We really need to use a second one to find that. And so, right, so what about the z equals 2,000? So the z equals 2,000 contour is, we know the slope already, right? So we can just use that point. What point does the z equals 2,000 contour go through? 100, 100. So it contains the point 100, 100, and also has slope negative 2/3. So that's y minus 100 equals negative 2/3 times x minus 100. We can play the same game. And rearrange this. I think that, again, check my math, but I think I did that rearrangement correctly. So this is the z equals 2000 contour. Okay, now here's the part where we need some insight, which is how are we going to figure out? We want an mx plus ny plus b that's going to work to give us this equation when z is 4000 and this equation when z is 2000. Right, this should be the same as 2000 equals mx plus ny plus b, right? So there's still a little bit of, I mean, it's kind of an interesting, sort of an interesting conundrum, like how would you actually recover? We can sort of guess m and n, right? What are we guessing for m and n? 2 and 3. Although we have to be careful because it could be like 4 and 6 or 6 and 9 or anything that's in the ratio 2 to 3. And then we want, right. So how are we going to do this? You find an mn and b that works like, or like think about how you're going to go about this. There is something interesting in the way these numbers seem related to each other. Yeah, who said that? Multiply by 4? Where are you seeing that? 500 to the 2000, 1000 to the 4000. Multiply by 4. I mean, really what the b is the b is the value at 0, 0. So you might also be able to try to figure out like what the value would be here. And actually, let's see, if we go from here to here, we go from whatever this height is to 2000. If we go from here to here, we go from 2000 to 4000. So can you guess what height that is? Looks like it's height 0, right? So yeah, so I mean, there's a few things going on here. You can use some of the geometry of the picture. You can use some of the, you notice you notice that this is times 4 times 4. So in fact, if we just multiply this equation by 4, we get something that looks right. If we multiply this equation by 4, we get something that looks right if b is 0, right? So it looks like, yeah, I kind of want to say times 4 with b equals 0. And this also has a like times 4 with b equals 0, in which case you get, if you multiply by 4, we get m equals 8, n equals 12, and so maybe m equals 8, n equals 12, and b equals 0. Seems to work. Okay. I mean, I was sort of, honestly, probably the best way is to try to figure out like what the height of this point is, to figure out what your b is, and then try to make things work. But there was something worth noticing there about the ratio. It's an interesting game to try to figure out a function that has certain level curves and the function that works. So let me just write that down, and then we can check our answer just to make sure we're sanity check. So it looks like z equals 8x plus 12y. That's it, plus nothing. Yeah, so for example, when z equals 2000, we get 2000 equals 8x plus 12y. But like we said, we can divide through by 4 and get 500 equals 2x plus 3y. And so that works, right? And similarly for 4000, Okay. Fun. Some sense of fun. For some definition of the word fun, that was fun. Yeah, I mean, the space heat is kind of what you're looking for here. And I think maybe that idea of going from the 2000 to the 4000 and seeing like 2 points, you can sort of figure out the height of other points by doing that. Okay. Okay. Yeah. All right. So I think I'm just going to move on to functions of 3 variables. It's all the same to you guys. Sounds like a party. Okay. Let's just take a breath and drink some coffee. Iced coffee. Drink iced coffee all winter. Sometimes when it's like -20 outside, I'll have a hot coffee. And I usually am like, I would have liked the iced coffee. How many of you drink coffee? Okay. I didn't start drinking coffee till grad school. You guys are, new generation starts their vices earlier or something. How many of you drink coffee in high school? When do you start drinking coffee? Your summer camp counselor, how old are you? 16? Anybody start drinking coffee before 16? When did you start drinking coffee? 5? What? That's good. And you liked it? Oh, wow. Right, that's how you start. That's what I learned in New England. Like you start with Dunkin' Donuts and it's basically all cream and sugar. And then you start building up to liking coffee. But it's funny, the 5-year-old drinking coffee thing reminds me of like, my dad gave me beer when I was like 5 years old because I wanted to drink his beer and he let me taste it. It was like disgusting. And like, I basically don't drink now. So it's probably a good, I've like never really become a drinker. So give your children beer, that's my advice. Okay. Could have backfired though, like if the kid likes it a lot. That's what did I do? Okay, so yeah, let's talk about functions of 3 variables. Because we've done functions of 2 variables, but this is multivariable calculus. This isn't 2-variable calculus. So we need to think about what happens when we have functions of more than 2 variables. We could think about functions of like 27 variables, but let's throw a 4th variable in there. So let's draw a 4-dimensional space. X, Y, Z. Where am I going to draw W? Time. You can't draw a 4-dimensional space, right? So that's an issue, right? We have an issue that we're very limited beings. We only see in 3 dimensions. And so how are we going to end up? Well, it's funny because the answers are already in those outlines are there. But how are we going to end up trying to think about this? Well, I like to do a lot of like thought experiments in this class of like, what if we only lived in 2 dimensions? How would we cope? It would be weird. Because really, like I'm seeing a 2-dimensional projection onto my eyeball. So if we lived in 2 dimensions, you would all be 1-dimensional projections. So I would just see little like dashes, you would all be little dashes in my field of view. At least you can move around each other. If we were in 1 dimension, you'd only ever know 2 people in your life, the 2 people on either side of you. I don't know how that would work. There's also a problem that if we were 2-dimensional beings, like could we have a gastrointestinal tract? Because wouldn't that split us into two pieces? Sorry, it's really interesting to think about. We might have to just osmose things in and like absorb things. All right, you guys don't care about any of this. Okay, so what?
You wouldn't be able to have any volume.
Yeah, no volumes at all, so it wouldn't work. Flatland, yes. Flatland's a great book, great story. What it's about a person who goes, a 2D being who goes into 3D. And then what happens? They lose their mind. They're just a circle, but then they don't they somehow figure out that there's a third dimension? And then what happens? Do you remember? What's that? Yeah, so it's weird, right? Because if they moved to the third dimension, they could see like your organs and stuff. Because we could see, if we were looking at two-dimensional beings, we could see inside their skin. Because we'd be looking from the third dimension down into them. That would be messed up. There's a story I read also when I was like in middle school about a short story. It was like about a surgeon who had this like incredibly new technique to perform surgeries. And it was like really mysterious. And this character finally gets to go like observe the surgeon. And it turns out that he figured out how to move his hands into 4 dimensions. And so instead of going through the skin, he can go around the skin and just operate directly on like a heart or something without actually having to open up a person. So it's, so yeah, imagine there's 4-dimensional beings right now watching us and they're not seeing just, it gets disturbing. Okay, disturbingly intimate, I feel like all of a sudden what I'm saying. You can see all, all right, they can see a lot. Yeah, okay, sorry. So the point is like I'm trying to do this just because it's like it's an interesting thought experiment to think about going from like 2 to 3 dimensions, 3 to 4 dimensions. A lot of times going like, so a 2-dimensional being could sort of draw a contour map, right? So for like functions of 2 variables, a contour map fits in 2 dimensions. So they could sort of draw a contour map, but they couldn't draw the 3-dimensional graph. But at least like the contour map, they could get some sense of how the function works. And then there is the idea of using a time as an extra dimension. So something like, actually like those movies, those little animations I was showing you of like the contours changing, right? Like a 2-dimensional being could understand that. Like not seeing all the contours at once, but just seeing like individual contours changing through time, and then they can get a sense of like what the graph looks like. Does that make sense? So like that's kind of what we're going to do here, but up a dimension. So we can't graph in 4D, but we can look at 3-dimensional slices. So for example, like, and I mean, we could think about doing x equals constant, y equals constant, z equals constant cross sections, but mainly what we started to do is just think about w equals constant, so like contours. So contours here is where w equals constant, and you get a surface in 3D, right? In x, y, z space. That makes sense? So like an example we could imagine is something like, I mean, here's a basic function, just like x squared plus y squared plus z squared. We thought about z equals x squared plus y squared. We could do a similar, thing here with x squared plus y squared plus z squared. So yeah, so example, w equals x squared plus y squared plus z squared. So if you do this, you have, like if you think about individual, what are the contours? for example, like W equals 4. That corresponds to 4 equals x squared plus y squared plus z squared. What surface is that? What surface is that in space? Have we learned this? We may not have talked about it, yeah. It's a sphere. It's a 3D analog of a circle, right? If we take this away, we get a circle of radius 2. And this is the square of the distance from the origin, right? So this, if we took the square root of both sides, we get distance equals 2 from the origin. All the points 2 units away from the origin is a sphere. So we get a sphere of radius 2. W equals 2, we'd get 2 equals x squared plus y squared plus z squared. So we get a sphere of radius root 2. And et cetera. So each height, we would get a sphere. So again, you can't picture all the spheres simultaneously, but you can picture a movie of like the growing sphere. Right. In fact, I really should have put a link to the Mathematica notebook. Sorry, I have a Mathematica notebook for this, and somehow that just occurred to me. The ones that we were looking at last class. Was it last class? Or no, you know what? It's probably the handouts. Yeah, stuff like this. So share screen. Nope. Sorry, let me open this for a minute and then. Yeah, so I actually have some things like this here. I thought I had more of these, but sorry, let me share. Yeah. Okay, so this is plotting x squared plus y squared plus z squared equals w for various values of w. Like if you look at this little slider here, that is a w. And now doing negative values is kind of silly because x squared plus y squared plus z squared cannot be negative, right? So let me just do 0 to 5. Okay, so that makes sense what's happening. Oh wait, I should do 0 to 25. It's related. So, right, so I'm playing this like a movie. Right, and I mean, if I stop it anywhere, it's kind of and it needs time to render to be an actual sphere. But so if I stop at any height, that's the W. That's like I'm picking the W value, I get a sphere. So again, you can't really picture this, but you can sort of picture it as like, a movie of spheres or something like that. Just like if we go down a dimension and did it with, right, I think we did it here. We had something similar where, oh yeah, again, this was sort of like used to render, but they're circles, right? So we were getting the contour plot of the paraboloid, but just seeing individual contours. So it's almost like a movie where you're like, it's like you're scanning the bowl shape, the paraboloid shape. As a scanner, as the Z is moving up, you're getting different circles, and the circles are getting wider, but it's kind of slowing down how they're getting wider. It's making a bowl shape, So that's like 2D slices. It's like an MRI or something. This is like a 3D MRI of a 4D object. So it's a little bit harder to picture, but it is something kind of similar that the spheres expand quickly at first and then sort of start slowing down. So that's kind of one way to think about this. We could do, and there is actually a command to let you, to let you see all of them. Oops. Small. Oh, hello. So if you actually, there's this command contour plot 3D where it's showing you like you can't, they're kind of shells. It's actually kind of lucky that they're getting cut off at the boundary here, because you're basically seeing these are like different contours of the function at like different heights. It's like analogous to the contour map that we would have, where we would see like a lot of circles spaced out. You know what I mean? It's weird. It's just because we can't think in 3D, so we can't. I mean, in 4D, so we can't see like all of this simultaneously, right? So these are actually called level surfaces instead of level curves. Level surfaces. So it's important that we think about it that way. I'm tempted almost just to show you pictures, but the thing to realize, actually, let me go back to the board for a minute, is that, you know, not everything's a function, right? Like in the plane, not everything is y equals f of x, right? So again, I want to make like a philosophical point. So consider, in 2D, not every curve's of the form y equals f of x, right? That's only if it satisfies the vertical line test, right? Like you can't cut, but there's plenty of curves. There's plenty of curves where y is not a function of x, or y is not a function of x, or x is not a function of y. And in fact, like a circle is the kind of standard example, right? X squared plus y squared equals 1 or 4 or something. Or you can do anything. You could, you know, or you could do something horrible like x squared plus sine of xy plus e to the y minus x cubed plus x plus 3y to the 10th equals 5. I just made this up, but it's like something where x and y are completely horribly inextricable from each other, right? But there are points like this would, well, maybe there's, I mean, you could have something there's no point satisfy, but you know, you could sort of like, this does make some curve. This is an equation. It makes some curve. It's an equation. It makes a curve in the xy plane. And I guess there starts to be a philosophy of, rather than think of this, you know, because you can try to solve for like y equals plus the square root of 1 minus x squared and y equals minus the square root of 1 minus x squared, you know, like the top and the bottom half of the circle. But rather than do any of that, it's like, what if we just consider this as a level curve of a function of 2 variables instead? So yeah, consider as a level curve of, we could say like the function x squared plus y squared at height 1. Right, and so that's kind of a philosophical thing here, is that we're going to actually start to do this instead. Instead of thinking about an equation and trying to solve for y or x or something like that, or deal with it that way, we're going to actually just think of it as a level curve. And like all sorts of, any sort of weird equation we come up with in the plane can be thought of that way, as a level curve of a function of 2 variables. And there will be calculus reasons why it's helpful to do that. If you remember finding tangent lines to things like this, finding rates of change involved something called implicit differentiation. Who remembers implicit differentiation? From anybody do it? I don't know. It's a horrible thing that nobody likes when they do single variable calculus. It's like you try to have this thing of like try to find the change of y with respect to x, especially if the equation is more horrible. Like here, you could find if you could find a point, you could find the dy dx at that point. It's sort of horrible. It turns out that if you think about it this way, there's a much nicer, cleaner way to find the rate of change or the slope. So we're going to see that when we start doing calculus. So it's sort of just like a philosophical thing. Let's do this. And similarly, we can try to think of surfaces as level curves of functions of 3 variables. So similarly, surfaces in 3D are similarly, I mean, I should say analogously, surfaces in 3D are not necessarily of the form z equals f of x comma y or something like that, or x equals or y equals something like that, right? You know, for example, x squared plus y squared plus z squared equals 1. Right, again, you could solve for z and get the top half of the sphere and the bottom half of the sphere as a plus square root and a minus square root, but it's going to be better to consider, so consider as the level surface of a function of 3 variables. It's a little bit hard to sort of really justify like why we want to do this until we see the calculus reasons why. So I'm just sort of trying to put this idea in your head now. But I will show you a couple things. We've got about 6 minutes left. So I will show you a couple things, one of which is there's this picture in the book that I like. So I guess it's page 735. Real fast. And so this is some of the surfaces we're encountering, right? And so we've seen, these all have A's and B's, which kind of stretches and does things like that, but you could always just think about A and B equaling 1. So if A and B equals 1, you just get z equals x squared plus y squared, you get the bowl shape, which is called a paraboloid. Again, if you set A, B, and C equal to 1, you guys see that? If you set A, B equals C equal to 1 here, you just get the sphere. So you can stretch the x and y and z by putting those A, B, and C in. So you can get these like egg-shaped things if you want instead. These 3 are sort of interesting. I'm going to show you something in a second related to these hyperboloids. Planes, cylinders, we've already talked about a little bit. Highlight stuff here. And we've talked a little bit about when there's a function just of like when a variable's missing. We got like the trough. This one's on its side because it's y equals x squared. But so it's sort of nice just to look through these and sort of understand them all. Like certainly I mean, I didn't talk about this hyperbolic stuff, but well, these are the saddles. We've actually done this when A and B were 1, right? We had x squared minus y squared was an example we looked at. So it's worth looking at these. This one in the middle, though, these hyperboloids are weird. You can think of this as taking a parabola and revolving it around the z-axis. You can think of the bowl shape as just taking a parabola and revolving it around the z-axis, right? That kind of sweeps out the bowl shape. These you think of hyperbolas, which are these kind of the things with the slant asymptotes. If you remember those, and then you can like rotate those around, and you'll get this sort of thing. But it's a little bit hard to see. And I want to show you in Mathematica. Some of this is just starting to play with stuff, and then we'll see. So what if I change this actually? I want to change this to, I just want to put like a minus sign. Wait, where do I want to put the minus sign? Yeah, with right here. Put a minus sign right here, and I'm actually going to make this like negative 10 to 10. So this is x squared. This is the function x squared plus y squared minus z squared. Again, that's something that's brand new that we haven't had a chance to really think about, right? X squared plus y squared plus z squared, it's pretty easy to think, okay, we just get spheres. This is interesting. This is minus 10 as I play the movie, we get this thing. So again, we're trying to think of a 4D graph, but it's like a movie of a bunch of 3D slices. And it's really just setting x squared plus y squared minus e squared equal to different constants. And right, this is a positive constant. You get this thing that's called a one-sheeted hyperboloid. For negative constants, we get this thing which is called a two-sheeted hyperboloid. And maybe at the beginning of class on Friday, I'll talk a little bit about why we might expect to get these shapes. But then the interesting one is 0. What if I put in 0? We get x squared plus y squared minus e squared equals 0. Anybody have a prediction? Yeah, Charlie. Just touching at one point, right? Yeah, so you got these, so it kind of has to come together and touch right at 0. We actually get cone, because we really have x squared plus y squared equals z squared, which in fact I think you just encountered on the problem set on some level is like a cone, right? So in fact, or this is a double cone actually. So it's interesting, there's that transition point. So it's a really kind of a cool way to look at this. There's this whole family of surfaces that are all related to each other just by changing this constant. I might, like I said, at the beginning of class on Friday, maybe I'll do a little bit of like why we expect to get pictures like this for different constants, but I just kind of wanted to show you pictures. And you might look at this catalog of surfaces a little more. All right, let you guys go. Thank you. I have office hours now, and again, Thursday afternoon.